Let's imagine a piece of material where the density changes from left to right. The gradient of color represents this change. Each slice of the material has two properties, its thickness and its density. As we move the slice across the material, the thickness depends on its position, and the density depends on the thickness. Let's watch how these properties change as the slice moves. At any given point, the thickness changes smoothly as the slice follows, and the density updates accordingly. But how do we calculate the total change in density as the slice moves through the material? Now that we've seen how position affects thickness and thickness affects density, let's translate this relationship into mathematical terms. We can break this down into two parts. The inner function, g of x, which transforms position x into thickness u, and the outer function, f of u, which maps thickness to density. To calculate the total change in density as the position changes, we need two pieces. First, how thickness u changes with position x, represented by g prime of x. Second, how density changes with thickness u, represented by f prime of u. These two rates combine to form the chain rule, which expresses the total rate of change of f of g of x as the product of f prime of g of x and g prime of x. The chain rule lets us understand how changes in one variable cascade through a nested relationship. Now, let's see this visually on a graph. This is g of x, the function that maps position x to thickness u. As position x changes, the thickness of u varies smoothly. On the right, we have f of u, which maps thickness u to density. As the thickness increases, the density grows quadratically. Here's how it works. Position x determines thickness. U is equal to g of x, and thickness determines density through f of u. The chain rule combines these relationships. It tells us that the rate of change of f of g of x is the product of the rate of change of g of x with respect to x and the rate of change of f of u with respect to u. This graphical view illustrates how the chain rule connects nested relationships. Let's apply this understanding to solve problems. Let's explore two examples of the chain rule, starting with a polynomial function and then moving on to a trigonometric function. First, let's differentiate 3x squared plus 1 to the fifth. The chain rule tells us to treat 3x squared plus 1 as an inner function and u to the fifth as an outer function. The inner function is 3x squared plus 1, and the outer function is u to the fifth. The derivative of the outer function is 5u to the fourth, and the derivative of the inner function is 6x. Applying the chain rule, we multiply these derivatives. Finally, simplifying gives us the result. Next, let's differentiate sine x squared. Again, we'll use the chain rule. The inner function is x squared, and the outer function is sine of u. The derivative of the outer function is cosine u, and the derivative of the inner function is 2x. By applying the chain rule, we multiply these derivatives. And simplifying, again, gives us the final result. With practice, the chain rule becomes second nature. Try solving more problems like these to sharpen your skills. The chain rule allows us to calculate the derivative of nested functions by multiplying the rates of changes for the outer and inner functions. We've seen how the chain rule helps us understand nested relationships, combine changes, and solve real-world problems. We started with an intuitive example of slicing through material, analyze the chain rule graphically, and solve problems step by step. The chain rule connects change across multiple layers, making it one of the most versatile and powerful tools in calculus. Thank you for exploring the chain rule with me. I hope you found this journey insightful and empowering.